So hello and welcome back. In this section, we're quickly moving on from the introduction of momentum to starting to look at solving problems using the law of conservation of momentum. Okay, so before we talk about just momentum in terms of the law of conservation and what, let's look at what we said previously. We previously said that the momentum of an object is equal to the mass of the object times the velocity of the object. Now that's very important, right? Because once you know that the velocity of an object multiplied by the object's mass is the momentum of that object, we can now move on to something a little bit more complex, and that is the momentum of a system, right? So let me get up a whiteboard over there and just clear the screen and talk about what exactly is a system. Oops. What exactly is a system? Important definition to take down. Let's get a blue pen there. A system, if you haven't done this previously, it is a part of the world, right? That, that we isolate, uh, isolate in order to study it. Okay, and this it refers to the part of the world that we will study. Now, in general, when we talk about momentum, we isolate systems where we want to study momentum that usually involve collisions, right? Collisions is where something knocks into something else. And then where something breaks free from something else, we consider that to be an explosion. Okay, so when we deal with collisions and explosions, sometimes we isolate that part of the world in which the collision takes place, right? For that period of time in order to study that part of the world. And that's what we talk about a system. Now, when we start looking at the momentum of a system, we're going to look at each of the objects in the system, and then we're going to say, okay, well, the momentum of a system is just equal to the momentum, um, of each of those objects, right? So here we go. The momentum of a system, right? Oops. The momentum of a system. Let me just get a line going there. The momentum of a system, or the total momentum of a system, is the sum, right? The sum of the momenta. There's some English there. Momentum, it's plural, is momenta, right? Or if we had, for example, momentum, momenta, other words are like curriculum, curricular, right? Momentum, momenta, that's a plural. So the total momentum of a system is the sum of the momenta of each of the objects in the system, right? So if you have object A and an object B, let's just clear that there for a moment. Let's get a new page. If you have an object A, if you have object A over there and you have object B, and we say, okay, let's isolate this part of the world. Let's isolate that part of the world into something over there. There's my world. It's been isolated now. Okay, I'm going to say this is an isolated system, and you already know what's a, I think, let's just take out all those words. It's partially redundant of me to say it's an isolated system. Let's just call it a system, right? If it's a system, it already means it's an isolated part of the world that we're going to study. Now that's object A, and that's object B. Now to get the momentum of object A, we say P of A is equal to MA times VA, and the momentum of object B is PB, right, is equal to MB times VB. But now if I ask you find the momentum of the system, you're going to say, well, the definition of a momentum of a system is just the sum of the momenta of each of the things. So the P of the system is equal to P of A plus P of B. That's the momentum of object A plus the momentum of object B. And that's important to note. When you want the momentum of a system, just add up each of the momenta. Right. Okay. So now we come up to two things. The principle of conservation of linear momentum. And here's a nice definition for you. In an isolated system, the total momentum before a collision is equal to the total momentum after the collision. And this refers both to collisions or explosions, right? Okay, and then the second part is the law of momentum. The law of momentum says the following. Numerically, or rather in the form of a formula, it says that F net, or the applied resultant force acting on an object, is equal to the rate of change, that means it's something divided by time, of the object's change in momentum, or the change of the object's momentum. That means delta P. And this year we can consider the law of momentum. Now don't stress too much about it right now. Just make sure you take it down, engrave the noodle pattern, and commit these definitions to memory. That F net delta T is equal to delta P, or F net is equal to delta P over delta T. That's going to give you this thing over here. Okay, so this says the following, right? Sorry, my bad. Where was I? F net delta T equals delta P, or F net is equal to delta P over delta T. That gives you this thing over here. This here we consider the law of momentum. Right. Okay, so moving forward, I'm going to give you again a definition which really relates to the principle of conservation of momentum. It's a little bit easier way of saying it. It says the total linear momentum of an isolated system is constant, right? And that's one of the answers you can give in your examinations as is. When they ask you, state the definition of the law of conservation of momentum, you just say the total linear momentum, that means in a straight line, of an isolated system is constant. Okay. Now, what does this mean? Okay, it means it is conserved. It means the following. It means delta P is equal to 0. That means that there's no change in momentum. That's the same as saying P final minus P initial is equal to 0. The final momentum minus the initial momentum is the same. Is 0. Because if you have 2 minus 2, you're going to get 0. 5 minus 5 is going to be 0. What if I had cow minus cow? That is equal to 0. So that means before and after we got the exact same thing. So similarly, all of this is saying that P final is equal to P initial, or P before is equal to P after. Okay, so take that down, make sure you got it down, put it in your books, engrave the noodle pattern, commit it to memory. Okay,